Hello there, and welcome to Sleepy Science Vault. Settle in. Let your body sink a little deeper. And let your mind drift out into the quiet of space. The universe is a place of immense scale. And yet, for all its size, it is almost entirely empty. When you look up at the night sky and see those distant points of light, you might imagine the cosmos as crowded, as full of life and motion. But the truth is, the vast majority of space is just that, space. And somewhere, in all that beautiful emptiness, there are places where stars exist, where they cluster together, pulled by gravity, like embers drifting slowly toward each other. In the dark, these places are rare, extraordinarily rare. For two stars to ever meet, to ever truly collide, the universe must first arrange them. Just so. The odds are almost impossibly small. Think about that for a moment. In all the observable universe, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, a true collision between two of them is still a rare thing, like finding two raindrops in an ocean that somehow fall on the same exact spot. There are regions of space where the probability of such a meeting is slightly higher. Gradients of likelihood, invisible contour lines, written in gravity and time, closer to the dense hearts of galaxies, where stars press nearer to one another. The odds shift, just slightly, in favor of something extraordinary. And the environment around these stars changes everything. A star drifting alone in the quiet arms of a galaxy will almost certainly never touch another. But a star born in a dense cluster, in a crowded nursery of light and gas, lives a different kind of life. In the cores of these clusters, something slow and inevitable begins to happen. The most massive stars, the brightest ones, burn fast and die young. And as they go, they leave the core a little emptier, a little quieter than it was before. This is called core depletion. And it happens so slowly, over millions upon millions of years, that no single star ever notices. It is simply the long exhale of a stellar neighborhood, growing still. And yet, even as the cores thin out, the nature of what remains shifts. The way stars are born changes. The balance between large stars and small stars tilts ever so slightly. We call this the stellar mass function. And in regions shaped by great collisions, even this fundamental pattern bends. Some of the most dramatic survivors in these dense environments are not single stars at all. They are pairs, binary stars, two suns bound to each other, orbiting in a slow eternal waltz. In regions where collisions and close encounters are more common, binary systems come to dominate. The survivors, the ones who found a partner and held on. And for these paired stars, a quiet process has already begun. It is called dynamical friction, and it is one of the gentlest, most patient forces in the universe. Imagine a star moving through a sea of other stars. As it passes, it tugs on everything around it, just slightly. And in return, all those little tugs slow it down, just a little. Like walking through water. You still move forward, but the water remembers you were there and takes a small piece of your momentum with it. Over time, this friction, so gentle it is barely imaginable, causes orbits to decay, to spiral inward. And that is when something begins to change. Two stars that have circled each other for billions of years start to drift closer. Not quickly, not dramatically, but closer. Their orbits are no longer the same. The distances that once separated them are shrinking, breath by breath, age by age. And as they draw near, something else awakens. The gravity of one star begins to reach into the other, stretching it ever so slightly, like a tide, rising slowly on a distant shore. This is tidal resonance locking, and it is one of the most beautiful and quietly ominous things that the universe does. Tides on Earth are caused by the moon's gravity, pulling the oceans gently toward it as it passes. But imagine that same force acting on an entire star, on a body of plasma, hundreds of thousands of kilometers across. As two stars approach, they begin to raise tides in each other. Enormous bulges, flowing slowly across their surfaces, in response to the gravity of their companion. And over time, these tidal forces begin to synchronize the stars, locking their rotation to their orbit, so that each one always faces the other with the same side, the same face, turned toward its partner for eternity. And yet, even this locked and synchronized beauty is not stable, because orbits, especially binary orbits, are never truly simple. There are rhythms within rhythms. The orbital period of one pair of stars can begin to pulse in time with the orbital period of another nearby system. And when those rhythms align, when they fall into step with each other, something unexpected happens. This is orbital resonance. And in most cases, in the gentle interplay of planets and moons, resonance is a stabilizing force, a kind of cosmic harmony. But in a crowded stellar environment, where multiple bodies are pulling at each other, From all directions, resonance can become chaotic. Small perturbations, tiny nudges in an orbit, can be amplified over and over until what began as a gentle wobble becomes something far more dramatic. An orbit that was nearly circular begins to stretch into an ellipse, and then a longer ellipse, and then longer still. And with each pass, the two stars come closer to their inevitable meeting. Let that settle over you. Two stars, separated by distances we cannot truly comprehend, drawn together by forces so slow and so patient that they operated across billions of years. You are breathing slowly now, in and out. The universe around you is quiet and dark and vast, and somewhere in that darkness, two stars are falling toward each other, slowly, slowly, slowly. And so, the dance continues. We left two stars falling slowly toward each other, drawn by forces older than memory. And now, we follow them a little further into the dark before they ever touch. Something else is already happening out there in the spaces between. Not all stars in a binary system remain together forever. Sometimes, a close encounter with a third star, a wandering sun passing too near, can disturb the delicate balance of a paired system. The intruder's gravity pulls at one of the two orbiting stars, and if the geometry is just right, if the angle and the timing align, one star can be flung outward at enormous speed. This is called a binary ejection, and it is one of the ways the universe moves stars across vast distances. The star that is thrown free leaves its partner behind and streaks out into the galaxy, carrying with it a kind of memory of the encounter in the form of its velocity. These runaway stars travel for millions of years alone, and the one that remains, the one left behind, continues its slow inward spiral, perhaps toward a different fate, for a true three-body collision, for three stars to meet at the same moment, in the same place, is almost vanishingly rare. Even rarer than two stars colliding by an enormous margin. The universe tends toward pairs, not triplets. Gravity is patient and precise, and three-body systems are inherently unstable. They wobble, they shift. One of the three is almost always, eventually, pushed away. And yet, the mathematics allows for it. Three stars spiraling together in a chaotic and breathtaking finale. It has almost certainly happened somewhere In the deep history of the cosmos, in some ancient galaxy, long before our sun was born, three suns, meeting in a brief, catastrophic moment of light. But we are getting ahead of ourselves. Before the collision, there is the wobble, as a binary system draws tighter, as those two stars close the distance between them. Their orbits begin to precess. Precession is a slow rotation of the orbit itself. The shape of the ellipse remains the same, but it rotates like a wheel, spinning lazily around its own center. You may have seen this with a spinning top. As it slows, its axis begins to trace circles, leaning and wobbling in long graceful loops. A binary orbit does something similar. The whole ellipse turns over thousands of years. And this precession, this wobble in the path, leaves signatures in the light that astronomers can measure from billions of kilometers away. These tiny wobbles are a whisper from the system, saying something is changing, something is tightening. And as the orbit precesses, as the stars draw ever closer together, they begin to truly feel each other, not just gravitationally, but physically. Their surfaces begin to respond. Each star is made of plasma, a churning, bubbling, magnetically alive fluid, and the gravity of its companion begins to reach down into that fluid and set it turning. The rotation of each star begins to synchronize with the rhythm of the orbit, like two dancers who have circled the floor together for so long that without thinking, they begin to mirror each other. Their spins, their speeds, their surfaces, all begin to align in a slow and beautiful coordination. This is rotational synchronization, and it is one of the quiet signs that two stars are no longer truly separate things. They have begun to become a system, a single gravitational entity, still wearing two bodies, but already something more. And then the light begins to change. Astronomers watching close binary stars sometimes notice a subtle brightening, weeks or months before anything dramatic happens. It is faint, easily missed. A slight increase in the total luminosity of the system. This is called a photometric pre-flare, and it is the first visible sign that something immense is coming. The tidal forces between the stars have grown so strong that they are raising enormous waves on the surfaces of both suns. These waves, these great rolling mountains of plasma, carry energy upward, and that energy radiates outward as light, a brightening, a quiet warning. And around the pair, something else is gathering. As the two stars have spiraled closer, over thousands of years, their outer layers, their stellar winds, have been interacting. Streams of particles, blown off both stars, have collided and mixed, and settled into a vast, expanding shell of gas and dust surrounding the entire system. This is the circumstellar shell, and it is a record, a physical archive of everything the two stars have shed over the long years of their approach. When the astronomers look at these shells, they can read the history of the system like rings in a tree. Each layer, a different epoch, a different chapter of the story of two stars falling slowly toward each other. And now, we have arrived. The moment that everything has been building toward, across millions or billions of years. The two stars are touching, not yet merged, not yet one, but their outer layers, their photospheres, the bright surfaces we would see if we could stand nearby, are overlapping. And in that overlap, something is released. Energy. An almost incomprehensible amount of energy. To understand the scale, consider that our sun, in a single second, releases more energy than all of humanity has ever produced in all of recorded history. Now imagine the energy stored in two entire stars, in their gravity, in their motion, in the thermal pressure of their interiors. All of it beginning to find a new equilibrium. That energy has to go somewhere. And it goes outward. A shockwave forms at the boundary where the two stars first make contact. And it moves in all directions at once, not at the speed of sound, as we know it here on Earth, but at speeds only possible inside a star. Hundreds of kilometers per second. A wall of pressure and heat, tearing through stellar material. As it travels, it compresses everything in its path, squeezing plasma, superheating gas, driving the temperature up to levels that cause the material itself to begin to glow in ways it never has before. The shock wave moves through both stars simultaneously, reshaping them as it goes. On the surface, the convection zone, the churning outermost layer of each star, where hot plasma rises and cool plasma sinks in great slow bubbles, the size of continents, is overwhelmed. Normally, convection is a patient process, moving heat from the deep interior up to the surface over weeks and months. But now, that machinery is overtaken. The shock wave drives a surge of energy, so powerful, so sudden, that the convection cells can no longer contain it. Plasma erupts upward, not in gentle rising bubbles, but in violent columns, kilometers tall. Driven by a pressure the star has never experienced. And at the surface, in the chromosphere, the thin, glowing atmosphere that wraps each star, just above its visible surface, an explosion occurs. We call this the chromospheric explosion. And it is the first light, the first visible sign to the wider universe that something extraordinary has happened here. The chromosphere, already a region of magnetic storms, solar flares, and eruptions, is now flooded with energy. From below, it lights up, brighter than it has ever been, brighter than the star itself. For a brief, astonishing moment, knots of plasma, ropes of magnetic field, are hurled outward into space at tremendous speed. And the light, that light, begins its long journey outward. It will travel for thousands of years before any eye, anywhere in the universe, ever sees it. But it has been sent. The universe has been informed that two stars, which began their lives as separate things, are now forever one. Let that thought carry you like a slow current outward into the dark. Breathe in slowly and out. You are small and warm and safe. And the universe, in all its immense quiet, is turning around you without hurry, without end. The collision has begun, and the universe is doing what it always does, quietly, methodically, following its own ancient rules, down to the very last detail. We are going deeper now, into the interior of two stars, becoming one, into processes so fundamental, so far below any surface, that no light will ever carry news of them out into space. And yet they are happening right now, somewhere out there, in the dark, inside the collision, in the region where the two stars are pressing into each other. The magnetic fields are meeting. Every star carries a magnetic field, generated deep in its interior by the churning rotation of electrically charged plasma, like a great slow dynamo, turning and turning for billions of years. These fields thread through the entire star, looping out through the surface, arcing back in patterns of extraordinary complexity. And when two stars collide, their magnetic fields collide too. Field lines from one star meet field lines from the other, and in the place where they intersect, something remarkable occurs. The lines break and reconnect in new configurations. This is magnetic reconnection, and it releases energy in sudden, intense bursts, It happens on our own sun, on a smaller scale. And when it does, it produces solar flares, explosions of radiation and particles that can affect our planet from 93 million miles away. Now imagine that process, scaled up to the collision of two entire stars. The energy released by magnetic reconnection in a stellar merger is staggering. It heats the surrounding plasma to temperatures far beyond what either star could have achieved alone. It drives jets of material outward along the magnetic poles of the newly forming object, and it adds its voice to the growing chorus of energy pouring outward from the collision site. But deep inside, deeper even than the magnetic fields, something else is escaping. Neutrinos. Neutrinos are among the strangest, most ghostly particles the universe produces. They have almost no mass, no electric charge, and they interact with matter so weakly that they pass through almost everything without leaving any trace. Right now, as you lie here, trillions of neutrinos from our own sun are passing through your body every single second. They do not notice you, and you do not notice them. In a stellar collision, the temperatures in the core rise to such extremes that nuclear reactions produce neutrinos in almost incomprehensible numbers, a flood of them pouring outward from the center in all directions, passing through the surrounding stellar material as if it were not there. While light, generated in the deep interior of a star, can take thousands of years to bounce and scatter its way to the surface, neutrinos escape in seconds. They carry energy away from the core, directly, instantly, like a door quietly opening in the side of the universe, and letting some of the heat simply leave. This neutrino flood, this invisible river pouring outward through space, carries information about what is happening in the very deepest, most hidden part of the merger. Information we cannot see, but can, in principle, detect if we have the right instruments pointed in the right direction at the right moment. And this is where something wonderful enters our story. Because human beings, small and brief as we are, have found ways to understand these events without ever being anywhere near them. Using computers, using mathematics, using the accumulated understanding of centuries of science, we have built simulations, virtual stellar collisions, running inside machines here on Earth. These simulations cannot capture every detail. The physics involved is too complex, too multi-layered for any computer yet built to model perfectly. But they reveal things. They show us patterns, structures, behaviors, that we could never deduce from observation alone. They show us the shockwave, moving through the merging material, compressing it, heating it, reshaping it. They show us the magnetic fields, twisting and reconnecting in patterns of extraordinary beauty. And they show us something else, something that takes a moment to fully appreciate. As two stars press into each other, as their material mixes and churns, the plasma between them is not a clean, frictionless fluid. It has viscosity. Viscosity is resistance to flow, the quality that makes honey move more slowly than water, that makes thick oil cling to your fingers. In plasma, viscosity arises from the interactions between particles, from the magnetic fields threading through the material, and from the sheer turbulence of everything moving at once. And viscosity generates heat, as layers of plasma, moving at different speeds, slide past each other. Their internal friction, their resistance to that motion, converts kinetic energy into thermal energy, into warmth. This viscosity heating adds yet another layer to the already overwhelming energy budget of the collision. The merger is not just releasing the energy stored in gravity and motion, it is also generating new heat. From the simple act of mixing two different fluids, churning together, becoming one, and where the shockwave has passed through regions of gas, both inside and outside the merging stars, something else is happening. The gas in those regions, which had been cool enough for its atoms to be neutral, for electrons to sit quietly, orbiting their nuclei, is now being struck by radiation and pressure so intense that the electrons are torn free. The gas becomes ionized, every atom stripped of some or all of its electrons, leaving behind a hot, glowing plasma of bare nuclei and free electrons. These are the shock ionization zones, bright regions where the passage of the shockwave has transformed quiet gas into something luminous. If you could see them, they would glow in colors that our eyes are not evolved to appreciate. Ultraviolet light, X-rays, the deep radiation of extreme heat. Beautiful in their own way, in a register we can only imagine. And deep in the heart of the collision, something is happening that cuts against everything we usually expect. Normally, in the universe, entropy increases. Entropy is a measure of disorder, of how spread out, how randomized the energy in a system has become. The universe tends toward disorder, toward equilibrium, toward the slow spreading out of heat and energy and information across ever larger volumes of space. This is one of the most fundamental laws of physics, almost a philosophical statement about the direction of time. but in the core of a stellar merger. For a brief moment, entropy decreases as the two stellar cores approach each other, and the material between them is compressed, squeezed to extraordinary densities. The disorder in that region temporarily reduces. Energy concentrates. Structures form. Complexity arises from what had been simpler, separate things. It will not last. The universe will reclaim its tendency toward disorder in time. But for this brief moment, in the heart of two dying stars, the arrow of entropy points the other way. In this moment, this pause in the universe's long exhale, is what makes the merger not just a destruction, but a creation. Now let us watch what the stars become. Not all stellar collisions are the same. When two stars approach each other slowly, when their relative velocity is low, when they have had time to synchronize, to tidally lock, to raise great waves in each other's surfaces, the merger is gentler, a slow merger. In a slow collision, the two stars do not simply slam together. They flow into each other, gradually. First their outer envelopes, the cooler, less dense layers near the surface, begin to mix. The material flows between them, through the inner Lagrange point, the place in space between the two stars, where their gravitational pulls are exactly equal, like two drops of water on a glass, slowly sliding toward each other until they touch, and then, without any violence at all, become one. The result is a merged star, larger than either parent, with a new structure, a new composition, a new future. But when two stars collide at high speed, when they meet by chance, in a crowded stellar cluster, without the long courtship of orbital decay, without the patient synchronization of tides, the encounter is entirely different. The collision is violent. The two stars do not flow into each other. They strike. And the energy of impact is so great that material is not merely mixed. It is disrupted. Vast quantities of gas are flung outward into a surrounding cloud of debris. The stars themselves may be partially destroyed, their outer layers stripped away, scattered into space. What remains at the center is something dense and hot and strange. A core, surrounded by a halo of its own ejecta, cooling slowly in the dark. And yet, whether the merger is slow or fast, gentle or violent, something unexpected happens to whatever star survives. It becomes younger. This is the rejuvenation effect, and it is one of the more quietly astonishing things that stellar collisions produce. A star lives by burning hydrogen, fusing it in its core into helium, releasing energy, And as it ages, it gradually exhausts the hydrogen in its central regions, leaving behind a growing core of spent helium, no longer burning, no longer contributing. The star ages. The fire at its heart slowly dims. But when two stars merge, when fresh hydrogen from the outer layers is suddenly mixed inward toward the core, the star finds itself with new fuel where before there was only ash. The clock resets. The merged star may live for hundreds of millions of years longer than either of its parent stars would have on their own. It is born old, but given new life in the same moment. In stellar clusters, these rejuvenated stars are sometimes called blue stragglers because they appear younger, brighter, bluer than their neighbors, who were born at the same time. They have outlived their generation by merging with it. And inside this newly merged star, the mixing continues. In a normal star, the core and the outer layers are largely separate. Energy flows outward, but material does not easily mix between the deep interior and the surface regions. But in the churning aftermath of a merger, the convection, the great slow overturning of the stellar interior, overshoots. Normally convection stops at a precise boundary where the material becomes stable enough that it no longer needs to rise and fall to move heat outward. But an emerged star, still churning from the violence of its creation, the convection rolls push past that boundary, carrying material from the deep core up into regions it would never normally reach, and drawing surface material down into the fire. This is core overshoot mixing, and it reshapes the star's interior completely. Elements that were formed in the deep nuclear furnace are carried upward to be dispersed, eventually, into the space around the star, and fresh material is drawn downward into the core, where it will be transformed into something new. The merger is not just a collision, it is a complete reinvention. Two stars, with their separate histories, their separate compositions, their separate futures, have been dissolved and reconstituted as something neither of them could ever have become alone. Rest in that thought for a moment. The universe takes things apart, slowly and patiently, and puts them back together as something larger and stranger and more full of possibility than what came before. You are breathing slowly. The room around you is quiet. And out there, in the vast and patient dark, a new star is settling into its new shape, cooling slightly at the edges, burning brightly at the heart, and beginning the long, slow work of simply being alive. The merger has happened. The violence has passed. And what remains is settling slowly into something new. We have watched two stars become one. We have seen the shockwaves, the magnetic reconnection, the great churning mix of material that follows a collision. Now we stay a little longer with the survivor, because what happens next in the long quiet aftermath is just as remarkable as the collision itself. Deep inside the newly merged star, the helium that was already present in the cores of both original stars has now been brought together into a single, dense, hot region at the center of something larger than either parent ever was. And that helium is waiting. In a normal aging star, when the hydrogen in the core runs low, the core begins to contract, to squeeze inward under its own gravity. As it contracts, it heats, and eventually, the temperature climbs high enough that helium itself begins to fuse. But in certain stars, particularly those below a certain mass threshold, the helium core before ignition becomes what physicists call degenerate. Degenerate matter is matter under such extreme pressure that the usual relationship between temperature and pressure breaks down. Normally, when you heat a gas, it expands. The pressure rises. The gas pushes back, and a natural balance is maintained. But in degenerate matter, pressure no longer depends on temperature in the same way. So when helium fusion begins, when the nuclear fire ignites, and temperature starts to rise, the core does not expand as it normally would to cool itself down. Instead, the temperature rises, and the fusion rate increases, and the temperature rises further, and the fusion accelerates again in an uncontrolled, runaway cascade, until, in a fraction of a second, an enormous amount of energy is released all at once. This is the helium flash. It is one of the most violent events in the life of a single star and an emerged star, where helium has accumulated from two separate cores. The conditions for this flash may be reached faster and more intensely than in any ordinary star. The helium flash does not destroy the star. Not usually. The energy released restructures the core, lifts the degeneracy, and the star adjusts. But it is a moment of crisis. A moment where the star's interior, very briefly, loses control of itself. And then, the helium ignites properly, steadily. In the newly restructured core. Helium core ignition. The beginning of a new phase of stellar life. Burning heavier fuel. Deeper in the furnace. At higher temperatures. With a different light. The star has passed through its crisis. And come out the other side. Burning brighter. For having survived it. But not everything survives the merger intact. As the collision unfolded. As the shockwave passed through the outer layers. And vast energies churned through the envelope. The outermost material of the merged star. The cool, extended, loosely bound outer layers was pushed and heated, and in many cases, simply lost. This is envelope stripping, the gradual, or sometimes sudden, removal of the star's outer shell. Imagine a fruit whose soft outer flesh has been scraped away, leaving only the hard inner stone. The merged star, after losing much of its envelope, is smaller, hotter, denser than it would have been if it had simply grown by accumulation alone. Its surface temperature rises. Its color shifts toward the blue end of the spectrum. And this is one reason that the survivors of stellar mergers often appear younger than the stars around them. They are blue and bright and hot in a stellar neighborhood that has long since cooled toward red and orange. But there is another reason these survivors appear so unusual. And it has to do with something that has been building throughout the entire collision. Motion. Angular momentum. When two stars orbit each other, they carry momentum in their orbital motion, in their spins, in every kilogram of material moving through space. And when they merge, all of that momentum must go somewhere. It cannot be destroyed. That is one of the most fundamental laws of physics. Momentum is conserved. Always. In every interaction. At every scale. So when two orbiting, spinning stars combine their material into a single body, that body must carry all of the angular momentum of everything that came before it. And the result is a star that spins faster than almost anything else in the galaxy. This is the angular momentum surplus, the accumulated spin of two entire stellar systems, concentrated into one. Normal stars rotate slowly. Our own sun takes roughly 25 days to complete a single rotation. A sedate, gentle, unhurried turning. But a recently merged star may rotate so fast that it completes a full rotation in less than a single day, or faster still. At extreme rotation rates, something dramatic threatens to happen. The centrifugal force, the outward push that rotation creates, begins to compete with the inward pull of gravity. At the equator of the star, where the rotational velocity is greatest, material is flung outward with increasing force. If the rotation rate climbs high enough, if the star reaches what is called the breakout spin rate, the equatorial material can no longer be held down. It leaves, flung off into space, in a disk of hot gas, encircling the star's middle, like a ring, like a halo of expelled material, still glowing, still carrying the heat of the star it just left. And as this material flies free, the star itself sheds some of its excess momentum, settles slightly, and continues to spin, still fast, but no longer at the breaking point. This equatorial disk, this ring of expelled stellar material, is one of the observable signatures that astronomers look for when they suspect they have found a recently merged star, a ring of glowing gas around a hot blue star, turning slowly in space, like a memory of the collision that made it. And as all of this is happening, as the star sheds its envelope, expels its equatorial disk, restructures its core, something is changing in its light. A merged star, in the immediate aftermath of collision, is in a state of confusion. Its interior has been scrambled. Its structure is not yet settled. Energy is being transported in new ways, through regions that were never connected before. And for a period, the star may actually dim, not because it is releasing less energy, but because the energy cannot yet find its way efficiently to the surface. But this does not last. As the interior settles, as the new convection patterns establish themselves, as the core finds its new equilibrium, the energy begins to flow outward again, freely, powerfully, and the star brightens. This is the luminosity rebound, the moment when the survivor, after its period of confusion and adjustment, announces itself to the universe with a surge of light. It may become briefly one of the brightest stars in its stellar neighborhood, outshining companions that have been burning steadily for billions of years. A sudden, unexpected brilliance from a direction where before there were only two ordinary suns. And once the rebound has occurred, once the star has settled into its new configuration, it begins to evolve, but not as either of its parents would have. It evolves faster. A more massive star burns its fuel more quickly, lives a shorter, brighter life, and moves through its evolutionary stages with more urgency. The merged star, heavier than either of its parents, is now on an accelerated timeline, where a star of the original mass might have burned quietly for billions of years. The merger product may exhaust its fuel and move into its next phase in a fraction of that time. This is evolutionary acceleration. The price of the merger, paid in longevity. The star is given new fuel and a new lease on life by the rejuvenation we spoke of before. But it burns that fuel at a higher rate, and its total lifespan may ultimately be shorter. Life, even stellar life, finds a way to balance its gifts with their costs. And now comes a moment that the star cannot avoid. A choice. Though of course, stars do not choose. They simply follow the laws written into the universe at the very beginning. But from our perspective, watching from a distance, across billions of kilometers and years, it looks like a fork in a road. Two possible futures. Two different outcomes, depending on the precise mass and composition and rotation rate of the survivor. In one direction, the merged star evolves into a giant, expanding outward as its core contracts and its outer layers swell into a vast cool envelope, a red or yellow giant, enormous, luminous, and relatively brief. In the other direction, the star remains compact and hot, burning quickly through its fuel and ending its life in a far more dramatic fashion. This is the evolutionary fork, the branching point, where the future of the survivor is decided. The same collision, the same merger, can lead to very different stars, depending on details that are measured, not in human units, but in solar masses, and in the precise temperature of a helium core on a particular day, in a particular place. Billions of years ago, the universe is exquisitely sensitive to its own initial conditions. And then there are those survivors that we can actually see in the sky, in globular clusters, those ancient spherical collections of stars, some of the oldest objects in the galaxy. Astronomers have found something puzzling. Scattered among the old red and orange stars that make up the majority of the cluster are a handful of stars that look wrong. They are blue and bright and hot and young-looking in a cluster where everything else is old. They appear to have skipped or reversed the aging process that all their neighbors have followed. These are the blue stragglers, the stars we mentioned before, the rejuvenated survivors. They are blue because they are hot. They are hot because they are massive. And they are massive because two stars, at some point in the long history of their cluster, fell together and became one. They have straggled behind the rest of their generation, in the race toward old age, because the collision gave them new fuel, when their neighbors had already spent theirs. When astronomers count the blue stragglers in a cluster and map where they sit within the cluster's structure, they find patterns. More blue stragglers near the core, where stellar encounters are more frequent. Fewer at the edges, where stars have more room to live their quiet, solitary lives. It is a census of collisions, written in starlight. Each blue straggler, a monument to a meeting that happened millions or billions of years ago, before our solar system existed, before Earth had cooled from its own formation. Two ordinary stars, living ordinary stellar lives, until gravity, patient and unhurried, brought them together and made something extraordinary. Let your eyes close a little more, if they haven't already. Think of those ancient clusters, hanging in the dark, each one a city of 100,000 stars, most of them old, and quiet, and red, and scattered among them, here and there, the blue ones, the survivors, the ones that merged and were remade and shine on still, long past the time when all their neighbors have grown dim. You too are settling now. Your breathing is slower. Your thoughts are softer. The universe is very large and very old, and it has been doing this for longer than any number we could comfortably say, and it will continue long after the last blue straggler has spent its borrowed fuel and grown quiet and dark and still. Rest now. There is more to tell, but it will wait for you, right here, in the calm, at the edge of sleep. We are still here, together, in the quiet. The merged star is settling, burning steadily, turning slowly, in the dark. And now, we look more closely at the traces it leaves behind, the subtle signs, the whispered signatures that tell us everything that happened. If only we know how to listen. Astronomers have a tool, a kind of map that they use to understand stars and where they belong in the story of stellar life. It is called the Hertzsprung-Russell diagram, named for two astronomers who independently discovered that when you plot the brightness of a star against its color and temperature, something beautiful emerges. Stars do not scatter randomly across the diagram. They fall into patterns, into rivers and clusters of points that trace the paths of stellar evolution. Most stars, our own sun among them, sit along a graceful curving band called the main sequence, A river of ordinary stellar life, running from hot and bright down to cool and dim. And when you look at where the oldest stars, the most evolved stars, have drifted, you find them scattered away from that band into territories of the diagram that represent later, stranger phases of life. But merger survivors do not always sit where they should. They appear in the wrong place. Too bright for their color, too hot for their age, too young looking for the neighborhood they inhabit. These are the HR diagram anomalies, the stars that make astronomers pause and look again and quietly ask, what happened to you? Their position on the map does not match any simple, single-star evolutionary track, because they are not simple, and they did not evolve alone. They carry the history of two stars, compressed into one set of measurements, and no single line on the diagram was ever drawn to describe them. They are off the map, in the most literal sense, navigating by stars that were not charted for their particular journey. And it is not only their position on the diagram that is unusual. The merger that created them was not a perfectly symmetrical event. When two stars collide, they rarely meet absolutely head-on, with equal masses, at identical speeds, from exactly opposite directions. The real universe is messier than that. More interesting, more asymmetric. One star is usually slightly more massive, or slightly faster, or the collision happens at a slight angle. And all of those asymmetries, all of those subtle imbalances, are absorbed into the merged star and preserved. The survivor inherits the asymmetry of its own creation. This shows up in many ways. The star may rotate slightly tilted relative to the plane in which its parents orbited. Its magnetic field, reconstructed from the fields of two different stars, may be lopsided, stronger in one hemisphere than the other. Even the distribution of chemical elements inside the star may reflect the asymmetric mixing that occurred during the collision, with more of a particular element concentrated toward one pole or toward one side. The star carries the memory of the angle at which its parents fell together, written into its own shape and chemistry and field geometry for millions of years afterward. And deep inside, something else is resonating. Stars are not rigid. They are not solid spheres. They are vast, fluid bodies. And like any fluid body, they can oscillate. They can ring. Like a bell. When you strike a bell, it vibrates at certain frequencies, determined by its size, its shape, its material. Stars do the same thing. They have natural oscillation modes. And under the right conditions, they pulsate, expanding and contracting, rhythmically, in patterns governed by the same physics that governs sound waves, and ocean waves, and the vibration of a plucked string. In a normal star, the pulsation modes are determined by the star's internal structure, and they change gradually as the star evolves. But in a merger survivor, the violent restructuring of the interior can force certain pulsation modes to lock together. Modes that would ordinarily be independent find themselves coupled, vibrating in synchrony, reinforcing each other in a phenomenon called pulsation mode locking. The star beats with a particular rhythm that is the direct product of the collision that created it. And astronomers who observe these stars carefully over long periods of time can detect this rhythm in the subtle rise and fall of the star's brightness. A heartbeat encoded in light, sent across light years to telescopes on a small blue planet where patient humans sit in dark observatories and listen. But pulsations are not the only oscillations that a merged star experiences. In the immediate aftermath of the collision, when the interior is still churning, still adjusting, still finding its new equilibrium, there are aftershocks, like a planet after an earthquake, which continues to tremble for hours or days after the main event. The merged star oscillates in its own interior. These stellar seismic aftershocks, waves of pressure and density, propagating through the star's interior, can last for thousands of years. After the collision itself, they travel through the star, bouncing off internal boundaries, reflecting from the core, dissipating slowly as their energy is absorbed and redistributed through the stellar material. And as they travel, they do something important. They mix. They carry material from one region to another, nudging composition gradients, stirring elements that would otherwise remain separated for millions of years. The aftershocks are the collision, continuing its work long after it appears to have ended. And at the surface of the star, large-scale fluid motions are also underway. On Earth, in our oceans and atmosphere, there are waves called Rossby waves, named for the meteorologist Carl Gustav Rossby, who first described them. These are vast, slow-moving waves caused by the rotation of a spherical body. Waves that travel across entire ocean basins and encircle the atmosphere. At the planetary scale, they arise because the Coriolis force, the force that comes from living on a rotating sphere acts differently at different latitudes. And this difference creates a restoring force that drives the waves. Stars, being rotating spheres of fluid, can develop their own Rossby waves. But stellar Rossby waves are not small things. They are disturbances that can extend across thousands of kilometers of stellar surface, churning patterns of hot and cool plasma that drift slowly in the direction opposite to the star's rotation in a rapidly spinning merger survivor, where the Coriolis forces are extreme. These Rossby waves can grow to enormous scales. They modulate the brightness of the star as regions of slightly cooler or slightly hotter plasma pass across the visible disk, and they transport energy and material laterally across the surface in slow, grand, sweeping currents. If you could watch from a safe distance, from a comfortable vantage point, somewhere in the space nearby, you might see the surface of the merged star rippling in slow and stately patterns, currents of light and dark, moving like weather across an entire sun. But not all of the drama is on the surface. If there is a companion star nearby, a third star that survived the original merger, perhaps orbiting at a safe distance, it too has been changed by what it witnessed. The collision, even from afar, expelled material in all directions, and some of that material, some of those high-speed particles and radiation and chemical-rich gas, reached the companion. It rained down onto the companion's surface, deposited elements there that were forged in the violent mixing of the merger event, elements that the companion never produced itself. This is companion pollution, the contamination of a bystander star by the chemistry of a catastrophe it only observed. The companion now carries in its outer layers a record of the event, a chemical fingerprint of the collision that happened nearby, perhaps millions of years ago. And when we look at the light of the merged star itself, we find something else hidden in the spectrum. The spectrum of a star is its fingerprint. Every element in the star's atmosphere absorbs light at very specific wavelengths, leaving dark lines in the rainbow of the star's light, like barcodes written in color. From these lines, we can read the star's chemical composition, its temperature, its pressure, its velocity, with extraordinary precision. But in a merger survivor, the spectrum contains something unexpected. Ghost lines, faint traces of spectral features, at wavelengths that correspond to elements or conditions that no longer exist in the star's current atmosphere. These are the echoes of a structure that existed during or immediately after the merger, when the temperatures and densities were different, when layers that are now mixed were still separate. The light that carries these ghost lines was absorbed deep in the star's interior at the moment of maximum chaos, and has taken time to work its way outward. By the time it reaches us, the conditions that created it are long gone. We are seeing not the star as it is now, but the star as it was. A faint, lingering image of a moment already past. The universe, it turns out, keeps very careful records of everything that happens in its light. And finally, as all this chemistry is mixed, as the interior composition changes, as new elements are distributed through layers that were once pure, the way the star handles its own energy changes too. Opacity is the resistance of a material to the passage of light. Dense fog has high opacity. Clear air has low opacity. And the opacity of stellar material depends strongly on its composition and temperature. In the churning interior of a merger survivor, as elements are mixed into new configurations, as concentrations of certain atoms form in regions where they were never present before, the opacity of those regions can spike sharply. Suddenly, a layer of the star that light passed through easily becomes more resistant, more opaque. The light piles up behind this barrier, heating the material further until the pressure forces its way through. These opacity spikes ripple through the star's evolution in ways that can cause sudden brief increases in luminosity as dammed-up energy finally pushes through. They are the internal consequences of a new chemistry learning to coexist with an old structure. Two stars worth of material learning to be one star. And perhaps that is the deepest truth in all of this. The merger is not just a physical event. It is an integration, a long, patient, sometimes turbulent process of two separate things becoming something unified. The asymmetries inherited from the collision, the ghost lines in the spectrum, the seismic aftershocks still trembling through the interior, the chemical gradients slowly evening out, are all part of that process. The star is not finished becoming itself. It is still in the slow work of integration, and that work takes time, as all the most important work does. Let your breathing slow a little further. The star is working out there in the dark, patient and unhurried, becoming more itself with every passing million years. And you are here, warm and quiet and still, drifting slowly like a blue straggler through a sky full of older light, finding your own way through the gentle dark towards sleep. We have spent time inside the star, watching it settle, watching it integrate, watching it become something new. And now, we step back a little further. We widen our view and look at the space around the collision, because the merger did not only change the stars, it changed everything nearby. It sent material outward into the surrounding dark, material that is now drifting, cooling, slowing, and beginning quietly to do something beautiful. But first, let us linger for a moment on the question of whether the merged star survives at all. Not every stellar merger produces a stable survivor. There are conditions, precise and unforgiving, under which the merged object cannot hold itself together. Imagine squeezing two balls of clay into one. If you press gently, slowly, the clay combines and holds its new shape. But if you squeeze too hard, if the forces involved are too great, the clay does not simply combine. It deforms. It tears. It may not hold at all. Stars behave similarly. There are stability windows, ranges of mass, rotation rate, and internal structure within which a merged star can find a new equilibrium, can settle into a configuration that gravity and pressure can maintain. Within these windows, the survivor lives. But outside them, in the regions of parameter space, where the merger product is simply too massive, or spinning too fast, or structured in a way that cannot support itself, the star approaches a threshold, the fragmentation threshold, the point at which the merged object cannot remain whole. At these extremes, the star does not settle. It breaks. Pieces of it, large pieces, shear away under the force of rotation or the pressure from within, and are flung outward into the surrounding space. What remains at the center may be far less massive than what first came together. The rest, scattered into the surrounding dark, to cool and condense, and eventually become something else entirely. The universe does not waste anything. It simply transforms it. And whether the merger produces a stable star, or fragments at the threshold, or somewhere in between, The space around it is now full of material that was once the outer layers of two suns. Let us watch that material as it travels outward during the merger, particularly in the final moments when the tidal forces between the two stars were at their most extreme. Great streamers of material were pulled free from the outer layers of each star. Imagine holding two balls of dough and pulling them toward each other quickly. The way the dough stretches and reaches toward the other ball before the surfaces touch. Stars do the same. Their outer layers, pulled by tidal forces, elongate toward each other, form bridges, form streamers. And when the collision finally occurs, some of this material, already stretched outward, is given extra velocity by the energy of the impact and flung further still. These are the tidal tails, long graceful arcs of stellar material, extending outward from the collision site in curving streams that may stretch for millions of kilometers. If you could photograph the merger from a great distance, in the moments after contact, these tidal tails would be among the most dramatic features. Two luminous arms, reaching out from the center, like the arms of a spiral, like the wake behind a boat, curving away into the dark. But the ejection of material is not the same in all directions. Just as the collision itself was asymmetric, just as the merged star inherited the tilt and imbalance of its creation, the material thrown outward is not distributed evenly around the merger site. More goes one way than another. More is concentrated in certain directions, less in others. This mass ejection asymmetry shapes everything that follows. The surrounding nebula, the cloud of gas and dust that will form from this ejected material, will not be a perfect sphere. It will be lumpy and directional and complex, reflecting the precise geometry of two stars falling together at a particular angle on a particular day billions of years ago. And as this material expands outward, some of it, the material that was not moving quite fast enough to escape entirely, begins to slow and spread and settle under the combined influence of the merged star's gravity and its own inertia. It forms a disk, not a perfect disk, not a neat, flat ring, but a broad, diffuse, slowly rotating structure, encircling the merged star at various distances. This is the accretion disk, or the merger disk, depending on its eventual fate, and it is one of the most fertile environments the universe knows how to make. Material in this disk rotates around the central star at different speeds at different distances, the inner parts moving faster, the outer parts more slowly, in the same way that inner planets orbit faster than outer ones. And as these layers, moving at different speeds, rub against each other, they generate heat, and they gradually lose energy and spiral slowly inward toward the star, some of it eventually falling back in. The disk is a slow, patient thing. It will persist for millions of years. And in the outer regions, beyond the disk, where the material is cooled enough, where the temperatures have dropped from the millions of degrees of the collision itself down to hundreds, and then to room temperature, and then colder still, the gas begins to condense, first into droplets, invisible, molecular, then into grains, tiny particles, smaller than a human hair, smaller than a bacterium. This is the dust cloud, the nebula, forming slowly in the cooling aftermath of the collision. And it is beautiful. If you could see it, it would glow softly, lit from within by the heat of the central star, scattering light in every direction, like a fog, illuminated from below. Different compositions, different colors, regions where carbon-rich grains make it dark and sooty, regions where silicate particles scatter a pale blue haze. It expands slowly over thousands of years, growing larger and thinner and cooler as it moves outward. Eventually, much of it will disperse into the broader interstellar medium, adding its contribution to the diffuse reservoir of gas and dust that fills the spaces between the stars. But some of it, some of the denser clumps, the regions where the material happens to be slightly more concentrated, will survive and may, in time, become something more, because the material in this cloud is not just hydrogen and helium. The collision mixed the interiors of two stars. It dredged up elements that were forged in nuclear fusion reactions over billions of years, deep in the stellar cores. Carbon, oxygen, nitrogen, magnesium, iron, all of them now drifting outward in this expanding cloud. And as the temperature drops, as the chemistry of the cloud slowly reaches the conditions where molecules can form, something remarkable begins to happen. Atoms begin to bond. They reach out to each other in the cold and quiet of the expanding nebula and form compounds: water, carbon monoxide, carbon dioxide, ammonia, formaldehyde, methanol, and among them, traces of molecules, far more complex, far more interesting, organic molecules, the building blocks of chemistry, as we know it here on Earth, forming in the wreckage of two colliding stars. The universe, in its long, patient way, is always making things more complex, more varied, more interesting, even in destruction. Especially in destruction, it plants the seeds of what comes next. And among the elements scattered into this cloud is one that carries a particularly intriguing story. Lithium. Lithium is one of the original elements produced in the first few minutes after the Big Bang, along with hydrogen and helium. It was there at the very beginning, but in the long history of the cosmos, lithium has been puzzling. Stars tend to destroy lithium. The temperatures in stellar interiors are high enough to break it down over time, and so as stars age, the lithium in their outer layers gradually diminishes. But in certain stellar mergers, particularly those involving stars of specific masses, something unexpected occurs. The violent mixing of the collision, the extreme temperatures, and the specific nuclear reactions that take place at the collision interface can actually produce lithium in significant quantities. Fresh lithium, created in the wreckage and expelled outward into the surrounding nebula. This lithium production is one of the ways stellar mergers may help to maintain the overall abundance of lithium in the universe, replenishing what stars have slowly been consuming over billions of years. But there is a deeper puzzle. Astronomers have measured the lithium abundance in very old stars, the most ancient stars we can observe, born in the earliest epochs of the galaxy. And they found that all these old stars contain roughly the same amount of lithium, a flat, consistent level, a plateau. This plateau, this uniformity, was considered a signature of the primordial lithium produced in the Big Bang itself, preserved in these ancient stars, like fossils, carrying the chemistry of the very first minutes of the universe. But more recently, astronomers have found old stars that break the plateau, stars with lithium abundances above what the Big Bang should have produced, or below what it should have preserved. And stellar mergers may be part of the explanation. The mixing and production of lithium in collision events scattered across the long history of the galaxy may have disturbed the uniformity of that ancient plateau, in ways that are only now beginning to be understood. Each merger, each collision, not only creates a new star in a beautiful nebula, but adds its own small chapter to the chemical history of the entire galaxy. Every collision, a letter written in lithium and carbon and scattered outward on the stellar wind to be read by patient scientists billions of years later on a small wet planet orbiting a very ordinary star. Let that sink into you. Slowly, the material drifting outward from that ancient collision is part of the same reservoir that eventually formed everything you see, everything you touch, everything you are. The carbon in your cells may have passed through not one, but many stellar collisions on its long journey from the Big Bang to you. You are here, breathing slowly, made of star stuff, including perhaps the stuff of stars that once fell together in the dark. The cloud is still drifting outward, cooling, thickening in places, thinning in others, making molecules, making dust, making, quietly, the raw material of everything that comes next. And you are drifting too. Slowly, softly, into the quiet. At the edge of sleep, the universe is working out there, as it always has, patiently, carefully, making something new from everything that ends. Rest now. There is still more to tell, and it will be here when you return. The cloud is still drifting, still cooling, still making its slow contribution to the space between the stars. And as we watch it go, we lift our eyes a little wider and ask a larger question. What does all of this collision and merging, all of this expelled gas and new chemistry, all of this lithium and carbon, drifting outward into the interstellar medium, what does it mean for the galaxy as a whole? The answer is everything. Galaxies are not static things. They are not simply collections of stars sitting in fixed positions, burning quietly until they burn out. A galaxy is a living system, a cycling, evolving, self-enriching environment where the death and collision of stars feeds the birth of new ones. When a stellar merger expels material, it is not lost. It joins the great interstellar reservoir, the diffuse cloud of gas and dust that fills the spaces between the stars, that makes up a significant fraction of the galaxy's total mass. And this reservoir is the raw material for everything that comes next. New stars form from it. They condense out of the cold gas. In regions where the density has crept above a critical threshold, where gravity has finally overcome the pressure that keeps the gas spread out. And these new stars, born from enriched material, carry within them the chemical legacy of every star that came before, every supernova, every stellar wind, every merger that contributed to the gas cloud from which they formed. This is galactic enrichment, the slow, generational accumulation of heavy elements in the interstellar medium over billions of years. The first stars, born shortly after the Big Bang, were made almost entirely of hydrogen and helium, the only elements the universe had yet produced. But as those stars lived and died, as they fused heavier elements in their cores and scattered them outward, the gas between the stars grew gradually richer. Each generation of stars, born from slightly more enriched material than the last, and stellar mergers, with their deep mixing, their dredged-up core material, their asymmetric ejections, are among the most important contributors to this enrichment. They are the events that scatter the heaviest and rarest elements, the ones forged only in the most extreme conditions, most efficiently, into the surrounding space. Every collision, every merger, every fragmentation is a gift to the next generation of stars and planets, and perhaps to the chemistry of life. And as the ejected material moves outward, something else is happening in the space it passes through. The merger has not only expelled gas, it has also accelerated particles, electrons and protons, flung outward at tremendous speeds in the jets and shockwaves of the collision. These high-energy particles, moving at significant fractions of the speed of light, spiral around the magnetic field lines that thread through the surrounding space. And as they spiral, they radiate not visible light, not the warm orange glow of an ordinary star, but radio waves, long, slow, deep electromagnetic waves that travel outward from the merger site in all directions. This is synchrotron radiation, named for the particle accelerators here on Earth, where it was first studied. And it gives the merger site a characteristic radio glow long after the visible light of the collision has faded, long after the optical brightness has dimmed, and the star has settled into its new equilibrium. The radio glow persists. Radio telescopes here on Earth, enormous dishes pointed at the sky, in quiet deserts and on remote hillsides, can detect this glow from collisions that happened millions of years ago in distant galaxies. The universe broadcasts on frequencies we cannot hear, but can learn to receive if we build the right instruments and point them at the right part of the sky and listen patiently for a long time. But what we detect depends enormously on where we are looking from. Two observers watching the same stellar merger from different positions in space would see very different events. If you were positioned along the axis of the jets, looking directly down into the beam of energetic particles pouring outward from the collision, you would see an event of extraordinary brightness, a brief, blinding flash of high-energy radiation concentrated directly toward you. But if you are positioned off to the side, looking at the merger from an angle perpendicular to the jet, you would see something very different. A slower, more diffuse brightening spread over a longer time as the expanding cloud of ejected material sweeps past you. This is viewing geometry, the profound effect of the angle between observer and event on what is actually seen. It is a reminder that what we observe is never the complete truth. It is always a perspective, a single line of sight through a three-dimensional event of enormous complexity. The universe looks different depending on where you stand to watch it. And now, we turn toward a different kind of collision, a stranger, more exotic kind. The stars we have been discussing are stars like our Sun, main sequence stars, ordinary stars in the prime of their lives. But not all stellar collisions involve ordinary stars. Some of the most dramatic, most consequential collisions involve stars that have already died. White dwarfs. A white dwarf is what remains when a star like our Sun reaches the end of its life. It has exhausted its nuclear fuel, shed its outer layers into a beautiful expanding shell called a planetary nebula, and left behind only its core. That core, compressed to roughly the size of Earth, but containing roughly the mass of the Sun, is a white dwarf. It is not fusing anything. It is simply a hot, dense ball of carbon and oxygen, slowly cooling over billions of years, radiating away the last of its heat into the dark. It will cool for longer than the current age of the universe before it finally becomes dark and cold. But what happens if two white dwarfs find themselves in a binary system together and begin the same slow orbital decay we described at the beginning? As their orbits shrink as they spiral closer. As the tidal forces grow, the outcome depends on one critical factor: their combined mass. There is a limit, called the Chandrasekhar limit, a boundary at approximately 1.4 times the mass of our Sun, beyond which a white dwarf cannot support itself against the crush of its own gravity. If two white dwarfs merge, and their combined mass stays below this limit, the result is a new white dwarf, more massive than either parent, perhaps with an unusual composition, a hybrid of their two chemistries, but fundamentally stable, cooling slowly, quietly, in the dark. If their combined mass approaches the limit, but does not exceed it, the outcome is uncertain, and the physics is complex, and the universe may take several different paths, depending on details that are still being debated by astronomers with great enthusiasm and large amounts of coffee. But if the combined mass exceeds the Chandrasekhar limit, something catastrophic occurs. The merged white dwarf cannot support itself. Gravity wins completely, and in a fraction of a second, the entire object collapses and then explodes. This is a type Ia supernova, one of the most energetic events in the observable universe. For a brief period, the explosion can outshine an entire galaxy, billions of stars, all at once, from the merger of two cold, quietly cooling, seemingly inert stellar remnants, comes an explosion of unimaginable brilliance. The universe, it turns out, has a very long memory and a very dramatic sense of timing. Among the most common white dwarfs are those made primarily of carbon and oxygen, the direct products of helium fusion in the final stages of a Sun-like star's life. These carbon-oxygen white dwarfs are the most likely candidates for the kind of merger that can produce a supernova, because carbon and oxygen are both fusible fuels under the right conditions. When two of them merge, and the combined mass exceeds the Chandrasekhar limit, the compression of the collapse heats the carbon and oxygen to fusion temperatures in an instant, and the resulting thermonuclear explosion tears the entire object apart. Nothing is left. No remnant. No stellar corpse. Just an expanding cloud of debris, rich in iron and nickel, and the heavier elements produced in the brief, furious nuclear burning of the explosion itself. This debris, this iron-rich cloud, expanding outward at a significant fraction of the speed of light, will eventually cool and join the interstellar medium, enriching it with elements that could not have been produced any other way. But not all stellar collisions involve objects of similar mass. Consider what happens when a star collides, not with another star, but with something smaller, something that almost became a star, but never quite made it. A brown dwarf. Brown dwarfs are objects more massive than planets, but not massive enough to ignite hydrogen fusion. They glow faintly in the infrared from the heat of their formation, slowly fading over billions of years. When a brown dwarf is captured by a star, or finds itself in a closed binary with one, and their orbit decays, the outcome is gentler than a full stellar merger. The brown dwarf, engulfed by the star's outer envelope, spirals slowly inward, depositing its mass and angular momentum into the star. Over a long period of gradual absorption, it does not survive as a distinct object. It is simply subsumed, incorporated, mixed into the star, as if it had never been separate. Its fate is quiet and complete, and the outcome of any merger, any collision, depends critically on the ratio of the two masses involved. When two objects of similar mass meet and merge, the collision is symmetric. The energy is shared. The mixing is thorough. But when the mass ratio is extreme, when one object is far more massive than the other, the smaller one is dominated, overwhelmed, tidally disrupted. Before the surfaces even touch, its material is stretched into long streamers by the gravity of the larger object, and accreted, drawn down onto the surface, or into the interior of its massive companion. Over an extended period, the larger object barely notices. It grows slightly. It may flare briefly as fresh material falls onto its surface, but it continues, essentially unchanged. The outcome of a collision is not just about the energies involved. It is about the balance between the two participants. And in the wreckage of any collision, in the expanding cloud of expelled and disrupted material, there are signatures, written not just in the elements present, but in the specific varieties of those elements. The isotopes. An isotope is a version of an element with the same number of protons, but a different number of neutrons in its nucleus. Carbon comes in several isotopes: carbon-12, carbon-13, carbon-14. Each one behaves nearly identically, chemically, but each one is produced in different proportions, under different conditions, in different nuclear reactions, at different temperatures and densities. The isotope ratios preserved in the ejecta of a stellar merger are a fingerprint of the specific conditions inside the collision. They tell us the temperature, the density, the duration of the nuclear burning with a precision that no other measurement can quite match. Meteorites formed from the cloud of gas and dust that surrounded our young solar system contain tiny grains, presolar grains, that preserve isotope ratios from events that happened before the sun was born. Some of these grains carry the signatures of stellar mergers, ancient collisions that happened billions of years ago in stars that no longer exist, preserved in millimeter-sized specks of mineral, sitting quietly in a museum drawer on a small planet in a very ordinary solar system. The collision, encoded in dust, waiting to be read. And sometimes there is no stopping what the collapse begins. When the merger product is massive enough and the conditions are right, the collapse does not pause. At the white dwarf stage, or even at the neutron star stage, it continues past every barrier, past every possible equilibrium, all the way to the ultimate endpoint of stellar collapse. A black hole. This runaway collapse, unstoppable, irreversible, is the universe reaching a kind of absolute conclusion, a place where the normal rules of space and time are stretched to their limits and beyond. The material of two stars compressed to a point of infinite density, surrounded by a boundary from which not even light can escape. It is the most dramatic possible ending to the story of two stars that began simply orbiting each other in the quiet dark, and at the other extreme, far from collapse, lies a different kind of consequence. When a merger produces an object of truly enormous mass, larger than any star that could have formed from a collapsing gas cloud alone, something between a very massive star and something stranger still, these ultramassive stars, products of multiple mergers, or the merger of already massive objects, burn with extraordinary intensity, radiating energy at rates that push against the fundamental limit of how brightly a star can shine. They are unstable. They shed mass in enormous outflows, driven by the pressure of their own light, pushing their outer layers away They live briefly, burning their enormous fuel reserves in millions of years rather than billions, and they end in explosions that can outshine entire galaxies. 4 days from the quietest merger, 2 small white dwarfs cooling in the dark, slowly falling together to the most violent, a runaway collapse, or an ultramassive star tearing itself apart with the force of its own light. The universe offers an extraordinary range of conclusions. Let all of that drift slowly through your mind, not as facts to be remembered, but as images to be felt. White dwarfs cooling in the dark, tidal tails curving outward, radio waves spreading across the galaxy like ripples on a still pond. The universe is very quiet in its largest motions. It does not hurry. It does not announce itself. It simply proceeds. And you are very small, and very warm, and very safe. Here, in the dark, while out there, among the stars, the long, patient, beautiful work continues. We have come a long way together through the quiet dark. We have watched ordinary stars fall slowly toward each other. Over millions of years, we have seen them merge and restructure and scatter their chemistry into the surrounding space. We have visited white dwarfs cooling and colliding in the deep dark of ancient clusters. And now, we arrive at the most extreme chapter of this long and patient story, the part where the universe reaches the very edges of what matter and energy and space and time can do. But first, one more consequence of the ordinary stellar mergers we have been tracing in the densest stellar environments, in the crowded cores of globular clusters, or in the brilliant hearts of young massive star clusters. Mergers do not always happen one at a time. A star that has already merged is now more massive than its neighbors, and a more massive star sinks toward the center of the cluster more quickly through the same process of dynamical friction we described so long ago. And at the center, there are more stars, and closer encounters, and higher collision rates. The merged star, more massive now, more dominant, encounters another star, and merges again. And the new object, larger still, sinks further, encounters more stars, merges more frequently. This is the runaway merger, a cascade, a chain reaction of stellar collisions, each one producing a survivor, more massive than the last, sinking toward new encounters in an accelerating cycle. Runaway mergers may be one of the pathways by which the universe builds objects of truly extraordinary mass, far more massive than any star that could have formed from collapsing gas alone. Some astronomers believe that the supermassive black holes sitting at the centers of galaxies, including the one at the center of our own Milky Way, may have grown, in part, through processes like this. A seed, a stellar merger, growing through further mergers and accretion across billions of years into something millions or billions of times the mass of our Sun, the largest structures in the universe, built from the smallest beginnings, one slow patient collision at a time. And now we arrive at the neutron stars. When a star far more massive than our Sun exhausts its nuclear fuel, it does not simply shed its envelope and cool gently into a white dwarf. It collapses, suddenly, catastrophically, in a fraction of a second, and then explodes in a supernova. What remains at the center, after the explosion has flung the outer layers outward into space, is a neutron star. A neutron star is one of the most extreme objects in the known universe. It contains roughly the mass of our Sun, compressed into a sphere, perhaps 20 kilometers across, roughly the size of a small city. At that density, a single teaspoon of neutron star material would weigh approximately 1 billion tons. Here on Earth, the pressure inside a neutron star is so extreme that the usual structure of matter dissolves. Electrons are pressed into protons, forming neutrons, hence the name, and the entire star becomes, essentially, one enormous atomic nucleus, held up not by nuclear fusion, not by thermal pressure, but by the quantum mechanical resistance of neutrons to being compressed any further. Now imagine two of these objects in a binary system together, two neutron stars, each one the compressed remnant of a star far larger than our Sun, orbiting each other at tremendous speed, circling dozens of times per second. They too emit gravitational waves, ripples in the fabric of spacetime itself, spreading outward at the speed of light in all directions. And those gravitational waves carry energy away from the system, causing the orbit to decay ever so slowly in exactly the way we have described before. But the timescale here is different. For two neutron stars, the orbital decay is faster, the final and spiral more dramatic, and when they finally merge, the energy released is almost beyond description. In a fraction of a second, the equivalent of several times the mass of our entire sun is converted into gravitational wave energy and radiated outward into the universe. In that brief moment, more energy passes through the surrounding space than our sun will radiate in its entire 10 billion year lifetime. And along the axis of the merger, something extraordinary forms. A jet. A narrow, tightly focused beam of material and energy, driven by the intense magnetic fields and the rapid rotation of the newly merged object, pouring outward in opposite directions at very close to the speed of light. These jets are among the most energetic phenomena in the universe. If you were positioned along the axis of the jet, looking directly into it, the event would appear to you as a gamma ray burst, one of the most brilliant flashes of radiation ever observed. A light so intense that it could be detected from the opposite side of the observable universe and surrounding the jet, expanding outward more slowly in all directions, is the Kilonova wind. A kilonova is the optical and infrared explosion that accompanies a neutron star merger. It is powered not by nuclear fission, as a conventional nuclear bomb would be, but by the radioactive decay of extremely heavy elements synthesized in the collision itself. For it is here, in the extreme densities and temperatures of a neutron star merger, that the universe makes its heaviest elements: gold, platinum, uranium, lead, the elements heavier than iron that cannot be built in the core of an ordinary star, are forged in the neutron-rich, extraordinarily dense, briefly superhot environment of a neutron star collision. The gold in a wedding ring, the platinum in a laboratory, the uranium in a reactor. All of it was made in a moment like this, in a collision of neutron stars, somewhere in the early history of the galaxy, billions of years ago. The Kilonova glows with the light of that synthesis, a soft red glow, as the newly made elements undergo radioactive decay in the expanding cloud. It is one of the most beautiful and one of the most meaningful lights in the universe. And inside the merged object, the magnetic fields, already extraordinary, are being amplified to levels almost beyond imagination. A neutron star already has the strongest magnetic field of any known object, billions of times stronger than the most powerful magnets we have ever built on Earth. But in the churning, differentially rotating, turbulent interior of the merger product, magnetic field lines are twisted and stretched and wound around each other at tremendous speed. This amplification can increase the magnetic field strength by orders of magnitude in milliseconds. The result: a magnetar, possibly an object with a magnetic field so intense that it distorts the structure of atoms near its surface and in the vicinity of this object. So dense, so massive, space and time themselves are distorted. Time passes more slowly in a deep gravitational field. This is not metaphor. It is a measured fact, confirmed by instruments on satellites and atomic clocks carried on aircraft near a neutron star merger product. The distortion of time is extreme. A clock placed close to the merged object would tick more slowly than one placed far away. The difference is not just theoretical. It is real, and it has consequences for every physical process in the vicinity. Even the behavior of particles changes in the flood of neutrinos pouring outward from the merger. Something subtle is happening. Neutrinos come in three types, called flavors: electron neutrinos, muon neutrinos, and tau neutrinos. And as they travel, they oscillate. They shift from one flavor to another in a quantum mechanical process that depends on their energy and the density of the material they are passing through. In the extreme environment of a neutron star merger, with its extraordinary densities and temperatures and gravitational distortions, these flavor oscillations happen differently than they would in empty space. They affect how much energy the neutrino flood carries away. They affect the neutron to proton ratio in the surrounding material, and therefore they affect which heavy elements are produced in the kilonova. The gold and platinum scattered outward in the merger's glowing wind owes its specific abundance, in part, to the oscillations of particles so ghostly that they pass through the Earth without noticing it, and in the most extreme conditions, at the very heart of the merger, where the densities are highest and the temperatures are beyond anything achievable in any laboratory, on any planet, in any solar system. Hints emerge of physics beyond what we currently understand. Exotic particles, states of matter, that may exist only in these conditions, only for milliseconds, only once in a billion years. In the heart of a stellar collision, the universe may be using these moments to do physics that we have not yet learned to describe. It is the edge of our knowledge, and it is humbling and wonderful in equal measure. But we do not have to imagine all of this entirely, because we have seen it. On the 17th of August, 2017, something remarkable happened. A signal arrived at the gravitational wave detectors of the LIGO and Virgo observatories. A ripple in spacetime, generated by two neutron stars, merging together 130 million light-years away in a galaxy called NGC 4993. The signal lasted approximately 100 seconds as the two stars spiraled together in their final spiral, and then merged. And almost simultaneously, gamma-ray telescopes in space detected a short burst of gamma rays from the same direction in the sky. For the first time, humanity observed the same event through two completely different messengers: gravitational waves and light. In the hours and days that followed, telescopes around the world and in space turned toward that small patch of sky in the constellation Hydra and watched as the Kilonova unfolded. They watched the blue flash as lighter elements were synthesized, fading within days. As the material expanded and cooled, they watched the red glow as heavier elements, gold, platinum, were produced and decayed in the expanding cloud. They measured, for the first time directly, the synthesis of heavy elements in a neutron star merger. They confirmed what theorists had long suspected, that events like this are the primary source of the heavy elements in the universe. The gold in the world was forged in moments like this one, observed on a quiet August morning by scientists sitting at computer screens, watching numbers change and knowing that those numbers meant something almost too large to absorb. This event, cataloged quietly as GW170817, is one of the most scientifically significant observations in the history of astronomy. A merger, 130 million years old, arriving at Earth as the faintest trembling in the most sensitive instruments ever built, and we were there to receive it. Let that land softly for a moment. A signal from a collision that happened when the dinosaurs had not yet evolved, when the continents were in different positions, when the ancestors of everything alive today were only just beginning their long journey toward the present. That signal has been traveling toward us ever since, at the speed of light, through the expanding universe, crossing 130 million light years of beautiful, patient, empty space, to arrive on a Tuesday morning in August at a detector in Louisiana. And we heard it. Breathe that in. Slowly, the universe spoke, and we listened. You are warm, and quiet, and very small, in the most wonderful possible way. Outside, the stars are turning, as they always have, as they always will, long past the time when anyone is here to watch them. But tonight, you are watching from the warmth of your bed, with your eyes gently closed, and the universe is telling you its stories, one slow breath at a time. We have arrived at something very specific now, something grounded, something real. We have spent a long time moving through principles and processes in the beautiful abstract physics of how stars behave. But the universe is not abstract. It is made of particular things, in particular places, that have particular histories. And astronomers, patient and persistent, have found some of them. Before we visit them, let us sit for a moment with the honest difficulty of finding them at all. Detecting the aftermath of a stellar merger is not a simple thing. The universe does not label its events. It does not leave signs pointing to the site of a collision. It simply proceeds and leaves traces, subtle ones, embedded in light and chemistry and motion. For anyone patient enough to look, the challenges are considerable. Many mergers happened millions or billions of years ago. The immediate fireworks, the brief bright flare, the fast-moving ejecta, have long since faded or dispersed beyond detection. What remains is often a star that looks almost normal. Its unusual rotation, its strange chemical composition, its anomalous position on the HR diagram are the only clues. And reading those clues requires knowing what a normal star should look like at that age, in that cluster, with that mass, and then noticing that this one is different. The ghost lines in the spectrum, the opacity spikes, The asymmetric chemistry are subtle. They can be mimicked by other processes, confirmed only by careful, repeated observation and comparison with theoretical models built over decades. And for the more dramatic events, the neutron star mergers, the supernovae from white dwarf collisions, the timing must be right. A gamma ray burst, lasting seconds, requires a satellite pointed in roughly the right direction. At that specific moment, the universe does not repeat its performances for the convenience of observers. It is a reminder that everything we know about these extraordinary events has been earned by careful people, working patiently over long careers, building instruments and methods and theoretical frameworks, piece by piece, over generations. What we know is hard-won, and what we do not yet know is vast. And yet, there are places we can point to and say with confidence, something happened here. Let us go to them. In the constellation Vulpecula, the little fox, a faint and easily overlooked constellation, sitting in the rich star fields of the Milky Way, there is an object that has been observed for more than 350 years. In the year 1670, European astronomers noticed a new star appearing in the sky. In that region, not a supernova, not something as dramatic as that, but a star that appeared, brightened, over a period of weeks, and then slowly faded back into invisibility. For centuries, it was classified loosely as a nova, and largely forgotten. One of many historical stellar brightening events in the old records. But when modern astronomers turned sensitive instruments toward the location of that old event, they found something still there. CK Vulpeculae, as it is now designated, is surrounded by a complex expanding nebula of extraordinary structure. The nebula is not spherical. It is not the simple expanding shell of an ordinary stellar explosion. It is an hourglass, a beautiful, intricate, glowing hourglass of gas and dust, extending outward in two lobes, above and below a central waist, where a dense disk of material encircles what remains. At the center, this hourglass shape is the signature of material ejected preferentially along two polar directions, while being constrained in the equatorial plane by the disk formed from the merged material during or after the collision. It is the visual record of how the ejection was shaped by the binary nature of what created it. The merger of two stars, written in glowing gas, across a region several light years wide. When astronomers looked at the chemistry of the material in the nebula, they found something remarkable. The gas contains molecules that are not commonly seen in the remnants of ordinary novae or supernovae. Complex molecules, molecules that speak of a cooler, slower, more intimate process than a simple explosion. Molecules that form only when gas cools slowly enough, in conditions rich enough, in the right elements, to allow chemical complexity to develop. This chemical richness is one of the signatures of a stellar merger, of the deep mixing in the material ejected, not in a sudden violent blast, but in the extended aftermath of two stars becoming one. And the nebula is not static. It is not a frozen relic. It is still active, still moving, still glowing, still producing new emission. In certain regions, more than 3.5 centuries after the event that created it, C.K. Vulpeculi is still telling its story, still expanding, still radiating, still doing what the collision set in motion on some quiet night in the 17th century, when a few observant human beings looked up and noticed a star that had not been there before. Measuring the distance to C.K. Vulpeculi has been important, not just for understanding that particular object, but as a reference point, a marker for calibrating other measurements in the same region of the sky. The distance, measured through careful parallax observations and confirmed through multiple methods, places it at roughly 3,000 light-years from Earth, within our own galaxy, close enough to study in detail, but far enough away that when the event occurred, 3,000 years of travel still separated its light from the planet it would eventually reach. The event happened while people were building cities, while empires were forming, while human civilizations were still young, and the light arrived while those civilizations were approaching their middle age, and was recorded by people who did not know what they were seeing, but knew enough to write it down. We are grateful that they did. And now, we travel to a different object, in a different part of the sky, in a different kind of event, in the constellation Cassiopeia, the great W-shaped constellation that rides high in the northern sky. There is a nebula called Pa-30, discovered relatively recently and recognized only in the last few years. as something extraordinary. Historical records from various cultures describe a bright new star appearing in the sky in the year 1036, approximately 1,000 years ago. Different observers in different parts of the world noted its appearance in chronicles and astronomical records, and then, as it faded, noted its disappearance. For a long time, no remnant was convincingly identified with this historical event. But Pa 30, a faint, circular nebula in the right part of the sky, and with an expansion rate that traces back correctly to the right period, is now considered a strong candidate for what that ancient brightening left behind. And the object at its center is strange. It is a white dwarf, but a white dwarf with a chemical composition almost completely lacking in hydrogen and helium. Most stellar surfaces, even white dwarfs, retain some hydrogen. The lightest element, the most abundant in the universe, tends to float to the surface of a white dwarf in a thin but detectable layer. But the white dwarf at the center of Pa 30 has almost none. This hydrogen and helium deficiency is a signature of a very specific process, the merger of two white dwarfs in a violent collision that processed and expelled much of the light element material, leaving behind a core enriched in carbon and oxygen and heavier products, almost to the exclusion of everything lighter and the nebula surrounding it. Pa 30 is expanding very fast, unusually fast. The material in the nebula is moving outward at speeds of several thousand kilometers per second. This high expansion speed is consistent with a thermonuclear explosion, a type Ia adjacent event, powered by the violent fusion, ignited in the merger, rather than the slower, more modest ejection of an ordinary nova. 1,000 years ago, someone in China, or Japan, or the Islamic world, looked up at the night sky and saw a new light in Cassiopeia. They did not know what they were seeing. They may have been awed by it, or frightened, or simply curious. They wrote it down, and 1,000 years later, scientists using space telescopes and radio observatories and the accumulated mathematics of centuries understood what that light meant. The collision of two dead stars 1,000 years ago, briefly outshining the stars around them and leaving behind an expanding cloud, still moving outward at thousands of kilometers per second to this day. And finally, we visit something more intimate, more precise, more recent. WD0525 plus 526 is a white dwarf, a single white dwarf, sitting quietly in the constellation Auriga, at a distance of roughly a few hundred light-years from Earth, close enough, in cosmic terms, to study in extraordinary detail. When astronomers analyzed its spectrum, the light it emits, carefully, they found something that white dwarfs, of its mass and temperature, should not possess: carbon, in detectable quantities, in its atmosphere. White dwarfs, as we mentioned, tend to have surfaces dominated by the lightest elements: hydrogen floating on top, helium beneath, because heavier elements sink rapidly in the intense gravity of the white dwarf surface. Carbon should not be present in detectable amounts in a white dwarf of this type, unless something brought it there. And something did. The leading explanation is that WD0525 plus 526 is a merger remnant, the product of two white dwarfs coming together and combining their masses and their chemistries into a single object. The carbon, dredged up from the interior during the violent mixing of the collision, has not yet settled, has not yet sunk back below the surface. It is still there, lingering, detectable, a chemical ghost of the merger that created this object sometime in the relatively recent past. In stellar terms, this is what a merger remnant looks like. Up close. Not a bright explosion, not a dramatic nebula, not a gamma ray burst, just a quiet white dwarf with a small amount of unexpected carbon in its atmosphere. And that carbon, so subtle, so easy to overlook, tells the whole story, if you know how to read it. These three objects, CK Vulpeculi, with its glowing hourglass, still expanding after centuries. Pa 30, the remnant of a 1,000-year-old light, still racing outward at thousands of kilometers per second. And WD0525 plus 526, with its quiet, telling, carbon signature, are 3 chapters in the same long book, the book of what happens when stars fall together, written in light and gas and chemistry, across the sky. You can look up on any clear night and point toward Vulpecula, or Cassiopeia, or Auriga, and know that something happened there. Something slow, and patient, and dramatic. something that the universe has been building toward for billions of years. In some cases, and something that patient, careful, dedicated human beings have been learning to read, one careful observation at a time. Let that settle into you. Like warmth, the sky above you. Even now, even as you lie here, quiet and still, is full of stories. Every point of light, a history. Every dark patch, a place where something happened, or is happening, or will happen. In time, you do not need to know the details to feel the weight of it. The sky is old, and patient, and full, and you are here, small and warm, beneath it, breathing slowly, in and out, with the universe doing its quiet work all around you. As you drift gently towards sleep, we are near the end of our journey. We have traveled far from those first quiet facts about empty space and probability gradients, and the rare chance that two stars might ever find each other in the dark. And now, in these final moments, we slow down even further and gather the threads of everything we have seen. But first, one more surprising detail, one more quiet wonder, hiding in the data. The white dwarfs we visited, WD0525 plus 526, and others like it, carry chemical signatures of their merger history in their atmospheres. But sometimes, the pollution in a white dwarf's atmosphere comes from somewhere even closer to home. White dwarfs, cooling quietly in their long stellar retirement, are sometimes found to contain traces of elements that have no business being there. Magnesium, calcium, iron, silicon. These elements, heavier than hydrogen and helium, sink quickly in the intense surface gravity in a matter of days, or weeks, or at most, thousands of years. For them to be present in detectable quantities, they must have arrived recently, geologically recently, astronomically recently, within the last few million years, at most. And the source, almost certainly, is rocks, asteroids, or the remnants of planets that once orbited the star when it was still alive, and which survived through the star's evolution into its white dwarf phase. As the star shed its outer layers, the planetary system was disrupted. Orbits shifted. Objects that had been stable for billions of years found themselves on new trajectories, some falling inward, toward the newly exposed, intensely gravitating white dwarf at the center, and they were torn apart by tidal forces before they could reach the surface, broken into streams of rock and dust that formed a disk and gradually rained down onto the white dwarf's surface. This is atmospheric pollution, not from another star, but from a former planetary system. The white dwarf, quietly consuming the last remnants of worlds that once orbited it. The white dwarf, in its long cold retirement, is eating its own planets, or what is left of them, slowly, peacefully, grain by grain. It is a melancholy image, in a gentle way, the long aftermath of a solar system's life, folding quietly back into its star. And now, we step back, further than we have before. All this time, we have been watching stars, the collisions of sun-sized or larger objects burning with nuclear fire. But the universe collides things at every scale. Planets collide too. In the early history of a solar system, when the disk of gas and dust around a young star is still clumping, still assembling itself into the family of worlds that will eventually orbit in stable peace. The process is violent. Young planets, growing by accumulation, sweeping up smaller bodies in their orbital paths, sometimes encounter each other directly. Planetary collisions are not just theoretical constructs. We believe our own moon was formed this way. Approximately 4.5 billion years ago, a body roughly the size of Mars struck the young Earth at an oblique angle, and the resulting debris, flung into orbit, coalesced over millions of years into the moon that has been circling us ever since. Every time you look up at the full moon, you are looking at the aftermath of a planetary collision. The tides it raises in our oceans, the way it stabilizes Earth's axial tilt, the romantic glow it casts on quiet evenings, all of it traceable back to an impact billions of years ago. And this is not unique to our solar system. Around other stars, astronomers have observed the signatures of planetary collisions unfolding in other solar systems. Right now, when two large rocky planets, or two ice giants, objects like Uranus or Neptune, collide, the impact releases an extraordinary amount of heat. The merged object, or the debris cloud, if the collision is disruptive, glows. In the infrared, the warm glow of impact-heated material, radiating as it cools. This infrared afterglow can persist for thousands of years after the collision itself, and it is bright enough to be detected by space telescopes from light years away. Astronomers have found several candidate systems where a sudden brightening in the infrared, followed by a gradual fading, is consistent with the aftermath of a collision between planetary bodies. We are watching other solar systems going through their own versions of the chaotic youth that our own system experienced billions of years ago. And as the debris from these collisions spreads outward, it forms a cloud of small particles that can sometimes pass between us and the parent star. When this dust cloud transits, when it crosses our line of sight to the starlight dims slightly in a characteristic way as the irregular, clumpy cloud blocks a small fraction of the light. This dimming is another way of detecting these events from a great distance. A slight, irregular fading of a distant sun as the aftermath of a planetary collision drifts across our view. And some of these discoveries have not come from professional astronomers alone. Citizen scientists, amateur astronomers, people sitting at home with computers, reviewing publicly available light curve data from space telescopes, have been among the first to notice these unusual dimmings. One person, looking at a graph on an ordinary evening, sees a pattern that doesn't fit and flags it and sends it in. And the professionals look more closely and confirm that something real is there. A planetary collision in another solar system, discovered by someone who was simply curious and patient enough to look. There is something deeply moving about that. The universe, with all its scale, and all its violence, and all its extraordinary complexity, can be touched by quiet curiosity, by the simple act of paying attention. And now, we come to the ending, the largest view, the longest perspective. All of these collisions, all of these mergers, all of this expelled gas, and new chemistry, and scattered elements, do they add up to something larger than themselves? They do. In the spiral arms of galaxies, those beautiful sweeping curves of bright young stars and glowing nebulae, That gives spiral galaxies their distinctive shape. The stars are not evenly distributed. They are concentrated in regions where the gas is dense enough to collapse and form new stars. And the density of that gas is influenced by the merger events that have seeded it with heavy elements and turbulence and energy. Stellar mergers, with their powerful ejections, their shockwaves, expanding outward into the surrounding medium, can compress nearby gas clouds to the point where they collapse and begin to form new stars. A merger, in triggering new star formation around it, can influence the distribution of stars along an entire spiral arm. One collision, setting off a chain of new births across light years. In the slow language of gas and gravity, and in the clusters where we find our merger survivors, the blue stragglers, and the anomalous stars, the asymmetric nebulae, and the fast-spinning merger remnants, the kinematics, the pattern of motions, is different from what you would expect. If every star had lived its life in isolation, the mergers have changed not just the individual survivors, but the dynamics of the whole cluster. The mass distribution has shifted. Some stars have been ejected by the recoil of the collision. Others have been slowed and drawn inward. The whole system is different from how it would have been if every star had simply burned quietly, alone. Mergers shape communities, not just individuals. And here, at the very end, we reach back further than we have gone before. The first stars in the universe, the population 3 stars, as astronomers call them, were unlike anything that exists today. They formed from the pure, primordial gas of the young universe, hydrogen and helium, with almost no heavier elements, no carbon, no oxygen, no iron, nothing but the lightest things. And without those heavier elements, which act as coolants, allowing gas to radiate energy and collapse more efficiently. These first stars were enormous, hundreds of times the mass of our sun. Perhaps, in some cases, living brilliantly for only a few million years before dying in the most powerful supernovae the universe has ever seen. We have never directly observed a population 3 star. They are all long dead. Their light, from the very edge of the observable universe, from the very beginning of stellar time, is only just now becoming detectable to our most powerful telescopes. But we see their influence in the chemical abundances of the oldest surviving stars. The population 2 stars, born from the gas that the first stars enriched, and stellar mergers. Even among those ancient first stars, may have produced objects of such extreme mass that their influence echoes down to the present. The heavy elements we carry, the iron in our blood, the oxygen in our lungs, the calcium in our bones, are the accumulated gifts of every generation of stars that lived and died and merged before our sun was born. We are, in the most literal sense, made of the aftermath of stellar collisions, and the full signature of any merger is never captured in a single observation, in a single wavelength, in a single instrument. To understand a collision completely, you must look at it in visible light, in infrared, and ultraviolet, and radio, and X-ray, and gamma ray, and gravitational waves, and neutrinos. Each wavelength, each messenger, revealing a different layer of the same event. Visible light shows us the surface, the photosphere, the place where light last scattered before escaping to us. Infrared shows us the cool dust, the expanding cloud, the chemistry of the ejecta. Radio shows us the energetic particles, the synchrotron glow, the jets. X-rays show us the hottest gas, the shock-heated material, glowing at millions of degrees. Gravitational waves carry news of the innermost dynamics, the changing geometry of merging masses, bypassing all the gas and dust, and arriving at our detectors, clean and direct, from the very heart of the event. No single view is the whole picture. Every wavelength adds a layer of understanding, and this, perhaps, is the deepest lesson of stellar collisions. To understand something fully, you must look at it from every angle, in every available light, with every tool at your disposal. A merger seen only in visible light is a beautiful mystery. Seen in all wavelengths, it becomes a complete story. The universe rewards patience and multiple perspectives, and the willingness to keep looking long after you think you have seen everything. We have come to the end of these facts, these 100 windows into what happens when stars collide, and perhaps what stays with you as you drift deeper into sleep is not any particular fact, not the Chandrasekhar limit, or the Kilonova wind, or the isotope ratios in presolar grains, but the feeling of a universe that is alive and active and endlessly creative, even in its most violent moments. A universe that takes two stars, born separately, orbiting patiently for millions or billions of years, and brings them together slowly and makes something new, something more complex and more interesting and more chemically rich than what came before. A universe that wastes nothing, forgets nothing, and is always, in its long patient way, building toward something more. You are part of that building. You are made of what the stars discarded, and what they forged, and what they scattered in their long lives, in their dramatic deaths, in their patient, beautiful, inevitable collisions. The carbon in you has been inside stars. The iron in you was forged in a supernova. The heavier elements in you were made in a neutron star merger 130 million years ago or more. You are, in every meaningful sense, a product of stellar collisions. And here you are, at the end of all of this, warm and quiet and breathing on a small planet, circling an ordinary star in one arm of a spiral galaxy that contains hundreds of billions of other stars, each with their own histories, their own collisions, their own slow patient dramas, unfolding over timescales that make human life feel like the blink of a single eye. And yet, here you are, blinking, and that is extraordinary. The universe made something that can wonder about itself, that can ask, what happens when stars collide, and spend 2 hours listening to the answer, and feel something while doing so. That is not nothing. That is, perhaps, the most remarkable thing in all of this. Sleep now. Let the facts dissolve into images, into feelings, into the soft dark behind your eyes. 2 stars falling slowly toward each other across an ocean of space and time. The universe working quietly, as it always has, as it always will. And you, here, warm and still and safe and home. Good night.